So in section 1.4, we found the instantaneous rate of change or slope of a tangent line or the value of a derivative for a specific number, like the value of, we found the derivative at a number like 3. We found f prime of 3, which was nice. This told us the slope of a tangent line. For the word problem we did, it gave us a speed in meters per second at a specific value. But the technique that we learned in section 1.4, it makes for pretty clean algebra, but it's not very powerful because it only, for one value of x, for each value of x, if I want to find the slope of the tangent line, or equivalently the value of the derivative, or equivalently the instantaneous rate of change, I have to do that computation every single time. And that's not powerful enough. In this section, we'll learn how to replace the number that we were doing for the x coordinate of the point and make the x coordinate of the point x. So instead of doing one point that has an x of 3 and another point that has an x of 3 plus h, which will only find the derivative or instantaneous rate of change for x equal to 3, in this section, we're going to come up with a formula. We're going to create 2 points. One point is going to have an x coordinate of x. The other coordinate is going to have an x coordinate of x plus h. It's going to make for grungier algebra, but it's going to be more powerful. For a specific function, I will have a way for any value of x to find the instantaneous rate of change. So if for one function I wanted to do 2 different instantaneous rates of changes, from section 1.4, I'd have to do 2 separate computations. In this section, I'll do one computation that gives me a formula, and I'll be able to use that formula to do the instantaneous rate of change for every value of x. This is a little bit of review. We talked about secant lines and tangent lines in the last section. A secant line connects 2 points on a graph. A tangent line really just touches the graph in 1 point, and its slope is the instantaneous rate of change at that value at that point. I can say this a million times, but it wouldn't matter to me when I was a student, but all of these are going to be the same. A slope of a tangent line, the value of the derivative, and the instantaneous rate of change. These words are completely interchangeable, so we can use them anytime I see any one of these 3 resets of words: slopes of tangent lines, values of derivatives, or the instantaneous rate of change. All of those are exactly the same words. They have the same meaning with just different words. If I'm asked to calculate any one of these 3, because these have the same meanings, they're going to have the same formula. In the last section, in section 1.4, we had the slope formula for instantaneous rate of change. We found 2 points. One point had an x coordinate of a, the other point had an x coordinate of a plus h. We found the y coordinate of each point. And then we found the instantaneous rate of change for that value of x by doing y2 minus y1 over x2 minus x1. In this section, we're going to do exactly the same thing, except instead of putting a number in for a, we're going to keep the a at the letter x. And that is going to give us a lot more power, but cause a lot more grunge to get there. So this formula with the a replaced to x is the derivative formula, the formula for the instantaneous rate of change, the formula to find the slope of a tangent line. And instead of coming out to just a single number, which is actually the slope of the tangent line, the actual instantaneous rate of change, we're going to get a formula that we can use to find the value. And let me just do this by doing an example. So, I don't know how well this is going to show up, but let me try to blow this up. So below, it's not below because I paged this out to a second page. Below is a graph of a function and its tangent line at the point 3, 0. So what I've done is I've graphed a tangent line to a function at the point 3, 0, and I took the time to say, oh, this tangent line goes through the point 3, 0, which is the point that's tangent to the graph, and it has some random other point. And I said, find the slope of the tangent line. Well, to find the slope of any tangent line, if I know 2 points, it's just y2 minus y1 over x2 minus x1. So I took the 0.56 and the 0.30. I called the 0.30 my first point, the 0.56 my second point, subtracted the y's in the numerator, 6 minus 0 for the y's, subtracted the x's in the denominator, 5 minus 3 for the x's, and I got 3 for the slope of the tangent line. So this tangent line is m equal to 3. If I said find the value of the derivative at 3, that's the same as the slope of the tangent line. Because the x-coordinate of this is 3, the slope of the tangent line at the point 3, 0 is the same as the value of the derivative at x equal to 3. And specifically, it's 3. There's no work for this. Slope of a tangent line is the same as value of a derivative. I drew a tangent line, I found its slope. The value of a derivative, so if the function is f of x, then the derivative of the function is given by the symbol f prime of x. And if I want to ask the question, find the value of the derivative when x is 3, I just change the x to 3. The value of the derivative when x equal to 3 is the same as the slope of the tangent line. Slopes of tangent lines, instantaneous rate of changes, and values of derivatives 100% exactly the same. In this section, this is going to come up ridiculously often. So rather than having to recreate this x plus h quantity squared every time I see it, I'm just going to have this in my back pocket. Every time in this section I see x plus h squared, I'm going to change it to that. And let me show you how I figured this out. X plus h squared is x plus h times x plus h. So I'll do firsts are x times x, which is x squared. Outers are x times h. They're both positive, so I'm going to get 1 plus. And I'll sneak a 1 in front to make the algebra easier. Inners are h times x. They're both positive, so I put a plus sign. I write the x first and the h second just because that's what I'm used to doing. And there's an implied coefficient of 1. The lasts are h times h. And h times h is a positive h squared. I'm going to add the 1xh and 1xh and get x squared plus 2xh plus h squared for what x plus h quantity squared equals to. That's a big deal, a big lifesaver in this section. You should keep that kind of in your back pocket and pull that out whenever we need it. All right, so let's do this now. We're going to find f prime of 4, not using the strategy that we did in the last section. In the last section, I would have created 2 points. I would have created one point that has an x-coordinate of 4, another point that has an x-coordinate of 4 plus h. I would have found their y's and then found the limit as h goes to 0 of the slope of the line that connects those 2 points. That's what we did in the last section. In this section, we're going to do something that's more useful. And I'm going to find the formula that allows me to find this value for any value of x by creating 2 points. So anytime I want to find an instantaneous rate of change, or a formula for the slope of a tangent line, or the derivative of a function, I create 2 points. The first point, in this case, is going to have a generic x as its x-coordinate. The second point is going to have x plus h as its x-coordinate. This is no different than the last section, other than now the number, like 4, is turning to x. Let me get each of the y's. Well, the first y is no-brainer. The first y is just 3x squared minus 5x plus 4. That's given. So the first point, the x is this x, the y is this 3x squared minus 5x plus 4. I don't know what this random x equal to 2, that shouldn't be there. That's junk that I'll delete out. In the second point, its x coordinate is x plus h. Its y coordinate's going to be 3 times x plus h squared minus 5 times x plus h plus 4. This is where I'm going to pull this out. X plus h squared is that. So that I'm not going to multiply out every time that I see it. So this is going to be 3 times x squared plus 2xh plus h squared minus 5 times x plus h plus 4. The y coordinate of my second point's a monster. It's going to be 3x squared plus 6xh plus 3h squared minus 5x minus 5h minus 4. No like terms, which is really unfortunate. So my second point, its y coordinate is 3x squared plus 6xh plus 3h squared minus 5x minus 5h minus 4. I have my 2 points. Now I'm going to find the slope of the line that connects those 2 points and make the limit as h goes to 0. So instead of writing now f prime of some number, I'm going to write f prime of x, which is that value right there. I'm going to form a fraction, and in the numerator, I'm going to take this y, doesn't need to be in a parentheses, 3x squared plus 6xh plus 3h squared minus 5x minus 5h minus 4. That's y2. Now minus y1. The y1 needs to be in a parentheses because I'm subtracting a trinomial, and the subtraction applies to each of the 3 pieces, the 3x squared, the minus 5x, and the minus 4. In the denominator, I can just write h, or I can physically subtract the x's, x plus h minus x, and I'm doing the limit as h goes to 0. I keep forgetting that, but I always sneak it in at the end. That's kind of I forget things, and that's the thing I always forget. So f prime of x is the limit as h goes to 0 of this junk. The denominator is just going to come out to be h because the x's cancel. The numerator, I'm going to leave the y2, 3x squared plus 6xh plus 3h squared minus 5x minus 5h minus 4. I'm going to clear this parentheses. I'm going to make it minus 3x squared. This minus is going to change that sign to positive 5x. It's going to change that sign from positive 4, which it was. I don't even know where I have this work at now. I scrubbed it. That should be a positive 4 right here. This 4, when I brought it down, I don't know why. I saw this minus and I changed its sign. I shouldn't. This should be a positive 4 right here. That should be a positive 4. That should be a positive 4. You have to be so careful when you're doing this math, and I'm not good at being so careful. So I try to not skip any steps, and I try to show every bit of work. And one sign error, like I made here, this plus 4, there was no reason to change its sign. The minus didn't apply to it, but I changed its sign. Would have caused me bad things. And so now, this minus is going to make that 4 a minus 4. And this guy right here, this y is supposed to be that y. So this y is supposed to be that y. And now that 3x squared turns to minus 3x squared. That minus 5x turns to positive 5x. That plus 4 turns to minus 4. What should happen when we're doing these derivatives is in the numerator, every term that doesn't have an x should cancel. I mean, every term that has an h doesn't cancel. Every term without an h does cancel. This 3x squared and that minus 3x squared cancel. This minus 5x and that plus 5x cancels. And this plus 4 and this minus 4 cancels. You absolutely are guaranteed to have a mistake if when you do the subtraction y2 minus y1 in the numerator, there's any piece that doesn't have an h. If it doesn't cancel, you make a mistake. So now I get f prime of x is the limit as h goes to 0. The denominator is just h, and each of the 3 terms left in the numerator has an h. I'm going to factor out an h to save some real estate. The 6xh, when I factor out an h, becomes a 6x. The 3h squared, when I factor out an h, becomes a 3h. And the minus 5h becomes a minus 5 when I factor out an h. Now I'm going to cross out that h and cross out that h and get f prime of x, or the derivative of f of x, or the formula for the slope of the tangent line, or the formula for the instantaneous rate of change is 6x plus 3h minus 5. Now I'm going to plug 0 in and get f prime of x equals 6x plus 3 times 0 minus 5. The answer to part A, I used the definition of the derivative, or the formula to find the instantaneous rate of change, or the formula to find the slope of the tangent line. I'm going to get f prime of x is 6x minus 5. If you've taken calculus before, you know that there's a way to get from there to there in about a second and a half. And in chapter 2, I'll teach you that, but in chapter 1, we have to do limits. That's the end of part A. For part B, I need to just find f prime of 4. F prime of 4, I get by plugging in 4 for x. I'm going to go 6 times 4 minus 5. That's 24 minus 5. The answer to part B, f prime of 4, equals to 19. That's about as grungy as it gets. But there's always more that we ask. At the beginning, it feels like so much. But eventually it's repetitive. We keep asking the same thing over and over and over again. It's just when it's brand new, it's a lot to take in. But it's the same. All I'm doing is finding 2 points, find the slope of the line between the 2 points by doing y2 minus y1 over x2 minus x1. But those h's need to go to 0, so I sneak that limit in there and do the math. All right, next. Given this function that we just dealt with, and I know that its derivative is 6x minus 5. So it says, first, find a formula to find the slope of a tangent line. The formula to find the slope of the tangent line is just the derivative. This is the exact same function. The derivative that I found in this example is a formula to find the slope of a tangent line. So if I give you this same function and a different value of x, and I say find a formula or find an equation that will help you find the slope of a tangent line, that's just a derivative. A derivative is a formula that can find the instantaneous rate of change for any value of x, or equivalently, it can find the slope of the tangent line for any value of x. So this is the derivative, and it's a formula that can find the slope of any old tangent line. Next, find the equation of the tangent line. That's a little more heady. So I have a formula to get slope, and now I want to find the equation of the tangent line. Let me put it right on here. I want to find the equation of a tangent line when x is this -1. This is not so bad at all. To find an equation for any line, I need a point and a slope. And I don't have full either. I have the x coordinate of the point. I don't have the y coordinate of the point. I have a formula to help me find the slope of the tangent line, but I don't know the slope of the tangent line. So I need to do two things. I need to find the y coordinate of the point, and I need to find the slope of the tangent line. Y coordinates of points I get by using the original function. I'm going to use the function 3x squared minus 5x plus 4 to get the y coordinate of the point. I'm going to use the derivative 6x minus 5 to get the slope of my tangent line. So if I plug -1 in and do 3 times -1 squared minus 5 times -1 plus 4, plugging a number into a function gives a y coordinate. This is going to be 3 times 1 plus 5 plus 4. This is 3 plus 5 plus 4. The y coordinate of my point is 12. The slope of the tangent line when x is -1, I just take the -1, which is a value of x that's given, and plug it into the derivative. And I get -6 minus 5, which is -11. So now I have a point and a slope. And if I have a point and a slope, I could find an equation for a line really easy by just going y minus y1, which is the y coordinate of the point, equals the slope times x minus x1. So I'm going to find the equation of my tangent line by going y minus the y coordinate of the point, which is 12, equals the slope, which is -11, times x minus the x coordinate of the point, which is -1. This is going to give me y minus 12 equals -11. That double negative turns plus, so -11 times x plus 1. I'm going to clear my parentheses and get y minus 12, do -11 times x, which is -11x, -11 times 1, which is -11. I'm going to solve for y by adding 12 to both sides. This gives me y equals -11x plus 1. That's the answer to this part B. Find the equation of the tangent line when x equals to 1, x equals to -1. It's going to be y equals -11x plus 1. Let me show you pictorially what's going on. So I have the point -112, and I have the equation of the tangent line, and I have the function. This is a picture of the graph of the function. This is a function 3x squared minus 5x plus 4. I plotted the point -112, and this line has a slope of -11, which means if I go down 11 and over 1, down 11 and over 1, I'd get from point to point on the graph. So this is pictorially what I found. I found the equation of this tangent line. It goes through the point -112, and it has a slope of -11. Ah, 23 minutes. Ooh, is it time to take a break, or is it time to talk about marginal profit? Let's wait and do a part 2. I want you to be more fresh when we talk about marginal profit, because a lot of you are business majors, and marginal analysis is a big deal in business classes, and we touch on it just briefly in our class, and I want to make it at the front end of a video rather than buried at the end of a video.